Okay, excellent. So let's start from where we left off in the last class. So we were talking about, uh, we started looking at couple more theory, and as we kind of discussed last time, the goal of this exercise is to be able to understand how systems of cavities and waveguides interact with each other. And can we build some simple models that can allow us to understand the spectral properties of these more complicated systems, which is different from doing like a full electromagnetic simulation, right? And it gives us more interpretability into how the physics of the system is working. So, last class I very roughly introduced optical waveguides, and so I didn't really go into any details. I merely wrote down what properties these optical waveguides have, and we'll be using them to some extent in today's class. And the detailed derivation of these properties are present in your notes, so I would encourage you to read them if you haven't seen these before. So let me just very quickly review what were optical waveguides, right? So optical waveguides are essentially electromagnetic structures that can confine light in two dimensions and allow propagation in one dimension. So you can imagine some kind of a cross section of an optical waveguide. So it has a permittivity distribution that depends on the transverse coordinates, let's say x and y, right? But it doesn't depend on the longitudinal coordinate, the coordinate along which a propagation is happening. And for such systems, Maxwell's equations permit typically what are called guided modes, and these are the modes that are of interest to us. So these are modes that are confined in the transverse direction but propagate in the z direction. Z direction, and they're mathematically they resemble something that looks like this. So it's some function of x comma y, which is typically confined in the transverse direction. So it exponentially decays as you move away from the waveguide in the transverse direction, and you have an exponential I beta z, where this beta is the propagation constant of the waveguide, right? And so this is what we call the mode profile. And this is what is called the propagation constant. And both of these mode profile and propagation constants, you could typically compute from Maxwell's equations if you know what the permittivity distribution of the waveguides look like. In some simple geometries, you can do this analytically, but in a more general case, you can always compute these numerically, right? So the mode profile for dielectric waveguides, which are waveguides that are made up of real permittivity distributions, have a very specific form, as we looked at yesterday, or rather I told you yesterday, I didn't really derive this. So which essentially said that if you try and decompose this mode profile into its components that are perpendicular to the waveguide and parallel to the waveguide, so you have a transverse component, let's say ET, as a function of x comma y. So this is in the xy plane, right? So when I say in the xy plane, I'm referring to in which plane does the vector corresponding to the electric field lie. The mode profile only depends on x comma y. So as a function of space, it is not dependent on z, but it is a 3D vector. So it can still have components in the z direction, even if it doesn't depend on z, right? So you have a transverse field that depends on x comma y, and you had a z component, z hat, which is pi by 2 out of phase in general with the x and y, with the xy component, right? So this phase relationship is very important. So your transverse field is pi by 2 out of phase with your z field, and independently these are real fields. So this is a real field, and this is a real field, okay? And from Maxwell's equations, you could deduce what the magnetic field looks like. So you could write down the magnetic field of this corresponding to this mode profile. And that too had a very, very similar form, which is that it too has a real transverse component and a longitudinal component that's pi by 2 out of phase relative to the transverse component. Okay, so this was, of course, for the forward propagating modes. So this is for the forward propagating modes. And for every forward propagating mode, we could construct a backward propagating mode. So a mode that is propagating in the minus C direction instead of a plus C direction. And of course, there are many ways of doing this, of constructing this backward propagating mode, right? As you know, these modes are not uniquely defined. They are defined up to some arbitrary phase. So you could have many choices for this backward propagating mode. One simple way of constructing this backward propagating mode is to consider, is to note that if E satisfies Maxwell's equation for a real permittivity distribution, which is what we are going to be concerning ourselves with, then so does E star. Right? So this is a complex conjugate because you could just take Maxwell's equations and perform a complex conjugation operation on it, right? And because epsilon is real, so epsilon becomes equal to epsilon star, and epsilon, and therefore E star satisfies the Maxwell's equations for the exact same structure, right? So if this happens to be the case, then you could just conjugate your forward propagating mode and get a mode profile for a backward propagating mode, right? So note the conjugation, what the conjugation would do very importantly is flip this exponential I beta z. So it'll become exponential minus I beta z, and therefore it's a backward propagating mode. So your backward propagating mode, let's call this E minus, could also be written as E transpose star x comma y exponential minus I beta z, and your E transpose star now had a minus pi by 2 phase difference between the transverse and the longitudinal components. Okay. And you can again get the magnetic field corresponding to the backward propagating mode by using Maxwell's equations, and this would look somewhat different from the magnetic field of the forward propagating mode. Okay. So this is just like a very simple list of what the mode profiles would look like. Of course, to calculate these mode profiles specifically, you have to go and solve Maxwell's equations, but these are some general statements that you could make if you're looking at waveguide modes corresponding to a real permittivity distribution, right? And finally, we also had a mode orthonormality relationship. Right, and what this mode orthonormality relationship essentially said was that if you take the electric field, the transverse electric field corresponding to two different modes. So you take the transverse electric field for, let's say, the nth waveguide mode, and you take its cross product with the transverse magnetic field of the mth waveguide mode, right? So we are looking at now two different guided modes, not the same guided mode. So you can imagine the fundamental guided mode and the second order guided mode, and you compute this dot product and you integrate it across the cross section of the waveguide, right? So you take the transverse fields, you compute the cross product, and you integrate it across the cross section of the waveguide. Then this is going to be delta n comma m, right? So this is an orthonormality relationship that exists in between two different guided modes of the waveguide. Okay, so this again follows from the eigenvalue equation for the waveguide modes. I'm not going to go into details, but you could look at the course reader for this, right? So this is like a quick refresher on waveguides. I'm sure you guys have seen this if you have done guided waves class in your previous quarters, but this is all that we need for the purposes of this class. Okay. So any questions on this? Because it's just like a list of properties, so I didn't really do anything in detail. So, but if there are any questions, can answer them now. Okay, great. Okay, so as I said, so what we are ultimately interested in understanding is how these cavities and waveguides interact with each other, right? And for understanding how cavities and waveguides interact with each other, let us first begin by the most general model that we can think of for like these cavity waveguide system, right? So I have, some kind of, let's say some cavities, which can be coupled to each other or uncoupled. We're not making anything very specific at this point. And these cavities are being fed with inputs through some waveguides, right? So there are waveguides that are going towards the cavity, and then there are waveguides that are coming out of the cavity, right? So at a very, very general level, right? So you can think of this device as a waveguide-based device, right? So if you just black box this permittivity distribution and not really think about what's happening inside for the time being, what you essentially have is a n-port waveguide device, right? So assuming you have this is waveguide 1, waveguide 2, waveguide n, you have an n-port waveguide based device, right? So you can imagine sending in, you have each waveguide can give you an input into the cavity region, which is injecting a propagating mode into the waveguide. And then based on however the cavities interact with the waveguides and interact with themselves, there is some backward propagating mode that's coming out of the waveguide as its output, right? So we have some input signal B1 plus as a function of frequency, and you have an output signal B1 minus as a function of frequency, right? For each waveguide, and so on, right? So because this is a linear system, I expect that these inputs and outputs are related to each other by a linear operator. Be able to calculate these outputs, that is B1 minus to Bn minus, by simply multiplying the inputs with a matrix, right? And that matrix is called the scattering matrix. So we define the scattering matrix as a matrix that is giving you the relationship between the input and output ports of these. Of this waveguide based device. Okay, so this is essentially what you would write down. So just a linear transformation between the input and output coming just from the linearity of Maxwell's equations. And the scattering matrix in general, you can compute for a given structure, right? So if I give you a particular permittivity distribution, how would you go ahead and compute the scattering matrix? Well, you would say that let me excite one port at a time. So let me set this to 1 and let me set everything else to 0. To 0. And if you do this, you're going to get the first column of the scattering matrix, right? So in this case, your Bi minus of omega is just going to be Si1 of omega, right? So if you do perform an electromagnetic simulation in which you send in unit amplitude forward propagating mode in one waveguide, and you calculate all the modes coming out of the other waveguides and the first waveguide as well, you'll be able to calculate one column of the scattering matrix. And you can repeat this and get the entire scattering matrix. So the scattering matrix is essentially, you can think of it as a compact way of writing the solution of Maxwell's equations, only if you're only concerned with what's happening in the waveguide mode. So you're hiding whatever is happening inside the device and just looking at what the electromagnetic device governed by Maxwell's equations looks like an input and output system, right? So of course, we would then expect the scattering matrix to be very highly constrained by the Maxwell's equations, right? So for a given permittivity distribution, you will have one specific scattering matrix. So many properties of Maxwell's equations that electric and magnetic fields satisfy, they will imply certain properties in the scattering matrix, right? So this, as I alluded to last time, there are 3 important properties of the scattering matrix that we need to understand. So the first property is called energy conservation, right? And this works if your epsilon is real, right? So if your epsilon is real, so there is no loss and there is no gain, then you have a situation where you have energy conservation, right? So what does energy conservation really mean? Well, it means that the total amount of power going inside the waveguide should be equal to the total amount of power that is coming out of the waveguide, right? So that's very intuitively how we can think about it. So mathematically, how energy conservation looks like is that it is essentially saying that if I take the pointing vector, so your pointing vector in frequency domain is given by E cross H star, right? And I calculate the total amount of power that is coming out of any surface in the electromagnetic structure. So you choose any surface S, right? And you integrate the real part of this pointing vector, which gives you the amount of power that is flowing on average across the surface. So you integrate the real part of this pointing vector across the surface S, then this is going to be equal to 0 in the absence of sources inside the structure, which is what we are assuming, right? We are sending in waves in the electromagnetic waveguide, so we don't really have any sources sitting inside the structure. So if there are no sources inside the structure, if you draw a closed surface around the structure and you integrate the real part of the pointing vector across the structure, then what you're going to get is 0. So this is a property of Maxwell's equations. It applies for any energy conserving electromagnetic structure, right? Now, if you consider the specific device that we are looking at, which is a waveguide based device, so a bunch of input and output waveguides, and you have some kind of an electromagnetic structure in the middle, which is formed by some cavities, then you can choose a surface that intersects the waveguide, right? So imagine choosing the surface far away from the electromagnetic device, from the region of the cavity, so that you're only seeing the waveguide modes and you're not really seeing any fields of the cavity by themselves. So then, while performing the surface integral, you're essentially just going to look at the amplitudes of the waveguide mode, right? And you can show using the field modes that I gave you in the beginning of the lecture that this integral is just equal to sum over the power that's going. So let's assume that we are choosing our normal to be coming out. So power that's going out of the waveguide minus the power that's going inside the waveguide, right? So this is a very, very simple exercise. It makes perfect sense, right? So this integral is telling me how much power on an average is going into the device region, and that's just equal to the amount of power that's coming out minus the amount of power that's going in. So the amplitude square of the backward propagating wave summed over all modes minus the amplitude square of the forward propagating wave summed over all modes, right? And if my system is energy conserving, right, if the permittivity distribution is real, then this is equal to 0. Okay, so what this really means is that if you think of this entire thing as a vector, and this as a vector, is that the norm of the B minus vector is equal to the norm of the B plus vector, right? So where B minus is the scattering matrix S of omega times B plus, okay? And this should hold irrespective of what excitation we apply on our cavity, right? So irrespective of what B plus is, this should hold. I can send in any input ports and get out the B minus field using this equation, and the norm should be equal. So what would this imply? This would imply that your scattering matrix is a unitary matrix, right? So S omega is unitary, right?
I have a question on, you try to expand the pointing vector into multiple B square, but is there any dielectric constant involved?
In what sense? This holds for arbitrary permittivity distribution.
Yeah, so how do you expand then into B component?
Right, so yeah, we can do that. So that's very easy. So all that you say is that my electric field on this surface, right, is equal to sum over forward propagating modes, En plus sum over backward propagating modes, right? And your magnetic field is sum over forward propagating modes Hn plus sum over backward
Yeah,
propagating
that
modes,
makes sense.
right?
Sure.
And then you just have to write E cross H star, and you integrate over the surface, right? So if you assume that these surfaces are, you can choose your surface to be normal to the waveguide, right? That's completely up to you. And then you can use this orthonormality relation that I've written here, which involves, note, the orthonormality relation involves one electric field and one magnetic field. So it fits exactly the format that you want, right? Because your pointing vector is also E cross H star, right? So if you do this, then you immediately get the result that I've written here, right? So it's a very straightforward set of steps. So it's there in the notes. I'm not going through all the details, but you see how it would work out roughly, right? Okay, so energy conservation implies that the scattering matrix is unitary, right? So energy conservation is, of course, a consequence of the fact that the amount of power that I'm sending in is equal to the norm of my input amplitudes. The amount of power that's coming out is the norm of the output amplitude. And because your device, which is essentially multiplying your input amplitude by a matrix to give you output amplitude, is going to conserve this norm, the scattering matrix has to be unitary. Okay, so one important point that I would make here is that this expression for the power being equal to norm of input minus norm of output is only true if you have normalized your waveguide modes to have unity power, okay? Which is what this normalization condition here is doing, right? So if you look at what this essentially resembles is a pointing vector integrated over pointing vector corresponding to the waveguide mode integrated over the surface of the mode. And when your n is equal to m, we have set this integral to be equal to unity, right? So we have normalized every the amount of power in every waveguide mode to be equal to this to 1. So that power has to be 1, or it has to be the same, right? So it's only then that you can claim that your power is equal to sum of squares of amplitudes of your input, right? So if your power, if the waveguide mode power depended on the waveguide mode, then this will no longer be true, and you'll have to rescale your amplitudes slightly. So that's one important point to keep in mind. So I'll come to that in a minute. Okay. So the second property that comes from reciprocity, right? So reciprocity is, again, it's a property of Maxwell's equations, which can be framed in many different ways. So let's look at what is a source-free way of framing reciprocity, right? So we don't want to put any sources in our problem because we are looking at incident fields and scattered field problems. So if you take now, reciprocity relates two different solutions of Maxwell's equation. So for example, energy conservation related one solution. So it said that if E and H are electric and magnetic field that satisfy Maxwell's equations, then they have to satisfy this Poynting's theorem, right? Reciprocity relates two different solutions. So let's say, so following the notation in your notes, so suppose E sigma and H sigma is one solution, and E delta and H delta is another solution, right? So you can imagine two different solutions corresponding to perhaps two different choices of exciting the waveguides, right? So you can imagine one solution is if you excite the first waveguide with some incident field and you look at what is the total field, that is one solution of Maxwell's equations for that device. Another solution would be that if you excite maybe the second waveguide with some incident field and look at the total field. So you're looking at two different solutions of Maxwell's equations. Then because these satisfy Maxwell's equations, it is very easy to show the following symmetry property, which says that if you again take a closed surface S and you integrate E sigma, the electric field of the first solution, cross with the magnetic field of the second solution across the surface, right? So we are constructing something that looks very much like Poynting vector, but it involves electric and magnetic field of two different solutions, right? So you have E sigma cross H delta, that is equal to E delta cross H sigma. Okay, so it's like a symmetry property. It's saying that if you look at this Poynting vector constructed in between electric field of one solution and magnetic field of a different solution, and you swap the indices of the electric and magnetic field, then you end up getting the same result, right? As far as this integral is concerned, right? So this resembles very loosely resembles a symmetry property. Now, and not surprisingly, because this loosely resembles a symmetry property, what this implies is that your scattering matrix is also symmetric as a matrix, right? So to make this more concrete, so for our particular problem, which is a device and you have a bunch of waveguides going in and coming out, right? So let's choose two specific solutions to see what we can say about the scattering matrix. Again, this result is completely general. It holds for any arbitrary electromagnetic structure and any arbitrary electromagnetic field, right? But we want to say something about our waveguide-based device from this result. So what we could do is we could choose a solution sigma, which is one of the solutions, to be, let's say I excite through ith port, right? So I only excite the ith waveguide. So let's say this is waveguide I and this is waveguide J. Okay, so I only excite one waveguide, ith waveguide, it can be anything. So what is the electric field then? In the waveguide region, your electric field would be equal to, you'll have only one forward propagating mode, which is the waveguide mode of the ith waveguide, right? But in general, you'll have backward propagating mode coming out of all the waveguides, right? So you'll have backward propagating modes, J, sum over J, coming out of all the waveguides, right? And the amplitude of each of these backward propagating mode will be equal to an element of the scattering matrix, right? So you're basically your B plus, here we are choosing this vector to be 0, 0, 0, 1 at the ith position 0, 0, 0, right? And then if you multiply the scattering matrix, you're just going to access the ith column, right? So let me delete this so that this doesn't confuse you later on. So this is just equal to S of, you're just getting the jth column, so J comma I multiplied by EJ. Does this make sense, right? So you're exciting only one input and you're looking at what are the amplitudes of the backward propagating waveguide mode, which is essentially just your scattering matrix. And similarly for solution delta, and again, as I already remarked, but maybe it's a good idea to repeat that, this is only true for fields inside the waveguide. Waveguide region, right? So you have to be, so to speak, sufficiently far away from where your device is for this electric field to make sense. If you're very close to the device, then the electric field modes are not the only modes of which would be relevant to the device, right? So similarly, you can construct another solution, which is excite through the jth mode instead of the ith mode, right? So your E delta can be a very similar expression. So it'll be EJ plus, actually, let me write this as K instead of J so that we are not confusing J. So SK of X. Then you're now again going to have a very similar looking expression with the I replaced with J, right? So now you have two different solutions to Maxwell's equation. You can write down the magnetic fields similarly. So your H of sigma, for example, is going to be HI plus sum over K, SKI, HK minus. And H of delta is going to be equal to HJ plus sum over K, SKJ, HK minus. Right? So you have these two solutions and now you can plug this in. They have to satisfy reciprocity. So again, you can choose a surface that's very far away from the waveguide modes. Sorry, very far away from the device, and you can apply this reciprocity condition. And when you plug it in and again use the orthonormality of the waveguide modes, from here you will immediately get the relation that Sij is equal to Sji, right? So you just plug these in and this relation immediately will pop up. Okay, so this implies that your scattering matrix is symmetric. So this implies S is equal to S transpose. Right, so we have unitarity and we have symmetry. Unitarity came from energy conservation, and symmetry came from reciprocity. Okay, so one point that I would like to make about reciprocity, it's a rather confusing property. Many people get confused about reciprocity. This is independent of symmetry in the device. Okay, so let me let's put into words what this reciprocity is telling us. So what it is saying is that if you have a device, consider two ports, I port and port J, right? So you have one input port and one output port. You excite through the input port, right? So you excite with unit amplitude through the input port, and you look at what is coming out of the output port, right? So this is going to be SJI. This is going to be coming out of the output port, right? So you're exciting the I at input port and looking at the field in the J at output port. And in the second experiment, you do the reverse of this. So you excite through the Jth port with unit amplitude, and you look at what field is coming out of the Ith output port. So this is going to give you Sij. These two are going to be equal. That's what reciprocity is telling you. So the transmission as a complex number, and this is not magnitude, this is a complex number. So both amplitude and phase, if you excite through input, first one input port, look at the transmission in the output port, versus if you are excited through that output port and look at the transmission in your original input port, those are going to be the same. And this is independent of the symmetry of the device itself, right? So you could expect this kind of a property if your device looks symmetric, right? So if I have a device which, for example, if I was to just draw something that looks symmetric, right? Then you would expect that, yes, obviously this is going to hold, because if I flip this device around, it looks the same, so I would expect this property to hold. But even if this device is asymmetric, even if this device looks completely asymmetric, your reciprocity property still holds. Okay, so that's very important. Does this make sense? Are there any questions? So reciprocity is independent of the symmetry of the device. Yes, question?
Yeah, I have a question. So, but there are devices where this doesn't hold true, correct?
Yeah.
So
right. So
for any device. So what changes for those devices in which it doesn't hold true?
Yeah, that's a good question. It's kind of going beyond the scope of this class, but I can make a brief comment. So non-reciprocal devices, a whole class. In fact, this is a whole field of research, how you can break reciprocity in Maxwell's equations. And if you look at all of Professor Fan's work, it's Shanwei Fan's work, it's in this area of how you can break reciprocity and what are the consequences of breaking reciprocity in different physical systems. From a very fundamental standpoint, you will break reciprocity if you break the symmetry of your epsilon tensor, right? So if you have an epsilon, a permittivity tensor. So in general, although we will typically in this class work with scalar permittivity, so permittivities that we can describe by a single variable, right? A single scalar. In most materials in general, your permittivity is going to be a tensor. So you are going to have permittivities relating the x, y, and z components of the displacement vector to x, y, and z components of the electric field vector in different ways. So in general, your permittivity is a 3x3 matrix, right? So if your permittivity is symmetric as a 3x3 matrix, then reciprocity holds, right? So of course, the discussion that we have been having up till now is for a scalar permittivity, right? We are restricting ourselves to cases where the permittivity distribution is a scalar. So this holds almost naturally because epsilon is just a 1x1 matrix, or you could think of it as a diagonal 3x3 matrix with the same elements on the diagonal, right? But the moment you can do something which will violate this epsilon equal to epsilon transpose condition, then you will start violating reciprocity, right? So if epsilon is not equal to epsilon transpose, then reciprocity is violated. And the way that people do this in practice is by applying a magnetic field to material. So there are many magneto-optical materials in which if you apply a magnetic field, it creates an asymmetry in the permittivity tensor. So typically if you apply magnetic field, and this is the physics behind what are called Faraday rotators. So they are very, very commonly used devices in fiber optics where you're trying to rotate polarization of an incoming fiber mode. So if you apply a magnetic field, what you end up doing is you end up creating off-diagonal elements, which are complex. So these are complex off-diagonal elements. So you have some, let's call this some matrix A here, but they're complex conjugates of each other. So they are equal to A dagger. So what you end up getting is epsilon is equal to epsilon dagger, which is different from epsilon equal to epsilon transpose, right? So by applying a magnetic field, you can make the matrix asymmetric as a complex matrix, but it is Hermitian, so it still conserves energy. So it's still an energy conserving system, but it ends up breaking reciprocity in your system, right? So Faraday rotators are one commonly used device that break reciprocity. So they use it for things like optical isolation or for rotating polarizations and so on, right? So this is, from a very basic perspective, how you can break reciprocity, one method. But this, of course, method is not very useful for integrated optical devices because you typically can't apply very large magnetic fields in integrated optical devices to significantly violate reciprocity. So then there are other ways in which you can violate reciprocity. So one way of violating reciprocity that has been a subject of research is through modulation of permittivities. Let me be more precise. It's through temporal modulation of permittivities. Time modulation. So if you're able to change the permittivity of your device on time scales that are proportional to the amount of time your electric field spends inside the device, right? So it has to be on time scales comparable to the time scales at which your electric field is interacting with your device. So this is not modulation that is static in nature. So it's not turning on and off. It's not turning the device on and off, but you have to modulate continuously while the electromagnetic mode is interacting with your device. So if you can do that, then you again end up breaking reciprocity. So this also breaks reciprocity. So this actually breaks something more fundamental. It breaks time invariance, right? So when we typically think about electromagnetic systems, we are thinking about permittivity distributions that are not changing with time. What is changing with time is our excitation. So we are changing the electromagnetic fields that we are scattering off the permittivity distribution, but we are not really changing the permittivity distribution. So my systems are time invariant in nature, right? Can someone tell me what one consequence of time invariance is that we have used here? Where have we used time invariance here? So this is like if you guys are from an EE background, this is just like a linear systems question. We can try and make the class interactive. It's a bit awkward otherwise. Where do you think we have used time invariance up till now?
I mean, I guess if it's not time invariant, the scattering matrix would change over time.
Right. So that's one way of thinking about it. So because this is a time invariant system, I can think of the scattering matrix as just relating frequency omega to frequency omega, right? So time invariant system means that a Fourier transform description exists. So for a time invariant system, if I send in frequency omega in a linear system, I will get out frequency omega in my linear system, right? Does that make sense? But if you have a time variant system, then sending in a frequency omega would in general create new frequencies at your output. So your scattering matrix is not going to be something that can relate frequency omega to frequency omega. It is going to relate frequency omega at the input to all frequencies in general at the output. Does this make sense? So the fact that you can write the scattering matrix as a function of a single frequency is a consequence of time invariance.
Could you elaborate more on the relationship between Fourier transform and the breaking time invariance?
Yeah, sure. So this is actually a general linear system concept. This has got nothing to do with our system in particular. So if you think about a system, let's say you're sending in some function of time, you're getting in and getting out another function of time, right? So we can, if the system is time invariant and linear, assuming it's linear and time invariant, the output of the system is a convolution applied on the input, right? So your y of t is going to be some integral h of t, right? So any linear time invariant system you can think of as applying a convolution to your input, correct? So, right, so and you can see that this is time invariant, right? Because you could say that if I send an input x of t minus t naught, if I displace the input into time, if this convolution property holds, you can show that the output is just y of t minus t naught. Okay, so if you plug in x of t minus t naught here, you'll see that the output will just be y of t minus t naught. right? So which means that, if I displace the input in time, I am displacing the output in time as well. So the system is not changing with time. In other words, the time reference is irrelevant, right? However, so a consequence of this is that if you try and relate the Fourier transform of y and x, what you end up getting is that the Fourier transform of y is equal to the Fourier transform of h multiplied by the Fourier transform of x. This comes from this convolution property, right? So if your convolution property doesn't hold, then the system cannot be described by a frequency dependent transfer function h. Okay, so that was my comment on Fourier transform. So if you can write the input at frequency omega the output at frequency omega to be input at frequency omega multiplied by h, you end up getting that can only be done for a time invariant system, right? So for a general system that's only linear, you have to write this as a function of two arguments. So let's say you'll have something like this, right? So your h is no longer a function of single argument, but a function of two arguments. So this is telling me how the input at time tau affects the output at time t, right? That's what this is telling me, okay? And in this case, if you try and Fourier transform this equation, what you'll see is that the frequency omega would in general be affected by all the frequencies in the input. Okay, so you will not be able to get a simple function of frequency describing the response of the system, right? And the very fact that we have been thinking about our scattering matrix as a function of frequency means we are looking at time invariant system. Okay, does this make sense?
Yeah.
Okay, yeah, we can talk about this more in office hours as well. So, but to cut the long story short, the moment you apply time modulation, you end up breaking this time invariance property, right? And so you seem to be breaking something more fundamental, but if you design your time modulation properly, you can approximately get a scattering matrix between two different frequency, right? So you can look at this as like an active area of research, but let's say you apply a periodic time modulation. If you apply a periodic time modulation, then your frequency omega can only affect only certain output frequency, and then you can end up violating reciprocity. So it's somewhat more complicated than violating reciprocity based on this effect, but it effectively looks like a violation of reciprocity, right? So time modulation is another way. And finally, another way that people have been investigating is violating reciprocity by violating the linearity of your system. So if you use some kind of a nonlinear system, then you can get an effect in which you end up violating reciprocity in somewhat of it's not perfect reciprocity violation, so there are some caveats to it, but effectively you can achieve under some assumptions a very similar violation of reciprocity. Okay, so but if your permittivity is scalar, then you cannot do anything to violate reciprocity. Just by designing your device, you can't violate reciprocity. Okay, so that's very important. Okay, so let's take a quick break for maybe 5 minutes, and then we'll come to the last part, which is time reversal symmetry. Okay. So let's, yeah.
Could I ask some question about you say just changing the device cannot break the time reversal symmetry?
Oh, reciprocity.
Reciprocity.
Yeah, time reversal symmetry is easier to break. Yeah, but reciprocity is very hard.
So what's the justification of that? Why you can break the?
Well, it just comes from why you can break time reversal symmetry, or why you.
Yeah, versus reciprocity.
So time reversal, as we'll see, so time reversal symmetry you can break if you have some loss in your medium.
Yeah.
Reciprocity you cannot break if you have loss. Even if, as long as your epsilon is a scalar, right? It can be a scalar that has loss. It can be a complex scalar. Your reciprocity will hold.
Okay.
Right? So most of the devices that you imagine in which you basically pattern materials, if you take a material and you draw some complicated shape out of it, you're not changing the fact that your epsilon is a scalar.
Yeah.
Right? And therefore reciprocity holds. So that's why it's very hard. Right? Whereas if you introduce loss in your system, maybe by using lossy material, for example, you can violate time reversal symmetry.
Wait, I also have a quick question. Could you maybe go up a little bit on your screen, a little bit more when you wrote the state? Yeah. So no, wait. Yes, there. So
I can't hear you. Sorry. I think you're muted.
sorry, can you hear me
Yeah.
now?
Yeah, I
Okay.
can hear you now.
So when you write the expressions for the electric field, like E delta, so I'm not really sure. So why? So the first, why does the EK? Why is it EK minus? Shouldn't it be EK plus? Because isn't it that the scattering matrix you apply to like the plus, like the incoming to like get the outgoing?
Right, but you get the amplitudes of the outgoing waves, right? So you get B minus. When you write the electric field, you multiply B minus with the correct mode profile. So you're right. So let me write this in more detail here. So I think what you're getting confused by is that the way I've defined my scattering matrix is that I take B minus and I get B plus, right? So now what is the electric field? So the electric field looks like sum over amplitude of the forward propagating wave multiplied by the forward propagating mode profile plus amplitude of the backward propagating wave multiplied by the backward propagating mode profile. Right? So these are just the amplitudes of the forward and backward propagating mode profile. Right? So when I'm writing down electric field as a function of space, I will multiply forward propagating wave by the forward propagating mode profiles and backward propagating wave amplitude by the backward propagating mode profile, right? What the scattering matrix does is give me a relationship between these two amplitudes. Does this make sense? So, so when we are constructing these solutions, what we are saying is that I send in forward propagating wave in exactly the ith mode, right? Which is the reason why you only have one EI plus, right? If you write the total electric field, you just have forward propagating wave in the ith mode. And then you write down the electric field for all the backward propagating waves, which in general are going to come out of all the modes. And the amplitude of the backward propagating wave, as you rightly said, we get by multiplying the scattering matrix on the forward propagating wave amplitude. But when I'm writing down the electric field, I have to multiply those amplitude with the backward propagating wave electric fields. Does this make sense?
Yeah, that makes complete sense to me.
Okay,
Thank you.
excellent. Any other questions? Yeah, this is stuff that you might have seen in EE236. I mean, I'm pretty sure you've seen in EE236B if you've done the class. Probably more detailed and thorough explanations of this. I'm rushing through it a little bit. Yeah. Any other questions, guys? Okay. So should we start again? Can we start, or do people need more time?
Yeah.
All right. So let's start. So the last and final property is that of time reversal symmetry. And there is often massive confusion between time reversal and reciprocity, right? Because if you don't think about it properly, reciprocity seems like a time reversal, right? So when we were physically interpreting the result of reciprocity, what we were essentially imagining is that I take two ports of my device, I send in unit amplitude through the first port and look at what's coming out of the second port, record that complex number, and then I send in unit amplitude through the second port and look at what is coming out of the first port and record that complex number, and then those two are equal. That was the reciprocity said in words. But note that this is not a time reversal operation, right? Because what I'm doing is, what is a time reversal? A time reversal is if you take all the amplitudes coming out of your ports and then you send them back again, right? Whereas here, what we are doing is we are sending unit amplitude through the second port. And we'll talk about that a little bit more, right? So it's important to make distinction. This is not the same as reciprocity. So what does time reversal mean in Maxwell's equations? right? And this is, often we're going to use this when we are developing temporal couple mode theory. So it's worthwhile spending a little bit time on this. It's really simple. So let's think about time domain Maxwell's equation. So you have del cross E is equal to minus mu naught del H by del T. And you have del cross H is equal to epsilon naught epsilon del E by del T. Okay. So time reversal is essentially saying the following. So let's say that E of x comma t and H of x comma t are solutions of Maxwell's equations, right? So you construct some solutions where you can imagine, exciting them with some initial energy. Let's say you send at t equal to 0, you have some electric field, and you look at how that electric field evolves with time as governed by Maxwell's equations, right? So you get, right. So you get this solution of Maxwell's equations, E as a function of x comma t and H as a function of x comma t. So what does time reversal tell us? So time reversal symmetry essentially is a statement of the fact that if you consider the reverse process, so what is the reverse process? Reverse process is saying that instead of looking at E of x comma t, let me look at E of x comma minus t, right? So E of x comma minus t and minus H of x comma minus t are also solutions to Maxwell's equations. Okay, so this is one statement of time reversal symmetry. Okay, so this just follows from Maxwell's equations. You can verify this very easily with just one line of algebra, right? Because if you differentiate E of x minus t with time, you essentially get a negative sign because of the minus t, right? Does this make sense? And then that negative sign is compensated in the magnetic field component. And the same holds for the first solution, right? So this operation is called time reversal, okay? So visualize this. So you have some electric field as a function of time. And then to do time reversal, all that you're doing is you're running the electric field backwards, okay? So that's what time reversal means, right? So often, now this is a slightly subtle point, but we have to think about it a bit. What happens is that when we are writing electric field, when we are typically thinking about these equations, we are thinking about electric and magnetic field that are real, right? So these are time domain Maxwell's equations. So my electric field is a real vector, magnetic field is a real vector. So they're physically the field that I would observe, right? But in many situations, because it's a real vector, it is going to have, and if you think about it in frequency domain, so if you have a real function of time, then in frequency domain, sorry, the positive frequency and the negative frequency components are related to each other, right? So if you have a function of time that's real, then if you know what the function looks like in frequency domain from positive frequency, then the negative frequency are related, right? So if you have a real function of time, real f of t, then you know that f of omega is equal to f star of minus omega. Okay, so there isn't actually separate information in the positive and negative frequency. And oftentimes in optics, especially when we are studying these solutions, what we are essentially interested in is what happens to the fields at near some certain operational frequency, right? So you're looking at, let's say, a cavity, you're looking at a cavity-based system. So you're kind of exciting it near the resonant frequency of the cavity, okay? So in many cases, it's more convenient for us to work with what are called phasors, right? So they're complex magnetic field, complex electric field, which only have these positive frequencies in them. They don't really have negative frequency, right? So we often work with phasor solutions, which often would look like E of x comma t is equal to, with this is equal to the real part of your phasor, E tilde of x comma t. Right? And h of x comma t is equal to the real part of h tilde of x comma t, right? And these are complex. So these now become complex numbers and they're not real anymore. But these complex numbers only have the positive frequency part of my electric field. We throw away the negative frequency part because it's redundant information. Okay, so when, for example, when we'll formulate couple more theory, then we'll look at this this again, right? So, and of course, if time reversal holds for the real part, the time reversal can in general be you can in general hold for these phasors, right? Because these phasors satisfy the exact same Maxwell's equations. So the phasors satisfy exact same Maxwell's equations. Right, so you have del cross E tilde of x comma t is equal to minus mu naught del by del t h tilde of x comma t, and del cross h tilde of x comma t is equal to epsilon naught epsilon x. Okay, so they also satisfy Maxwell's equations, right? There's no problem here. So they also will satisfy time reversal symmetry, right? So which implies that phasor solutions also satisfy time reversal symmetry. Okay, and so let me just draw a picture here just so that we have this in mind. So essentially, if I look at E of x comma omega, right, the Fourier transform of Ex comma t, then you have some positive frequency contribution and you have an equal negative frequency contribution because it's real, right? So however much you have positive should be there in negative frequency as according to this relationship. For phasors, what we are essentially doing is that we are throwing away this negative frequency contribution. So from here you're calculating E tilde of x comma omega. Okay, so we only think about keeping the positive frequency. And clearly you can go back and forth in between these two, right? So if you know the original field, you can construct the phasors by just keeping the positive frequency components. And if you know the phasor, you can then replicate it on the negative frequency and construct your full solution, right? Which is what this operation is doing. Does this make sense? Okay, so your phasor solutions also satisfy time reversal. So you could say that, well, if E tilde and H tilde are solutions of Maxwell's equations, then so are E tilde. So if E tilde and H tilde are solutions of Maxwell's equations. So are E tilde of x comma minus t and H tilde of x comma minus t. Okay, so this again should hold because it satisfies the same set of differential equations. Your time reversal property should hold there. Okay, however, now one thing that happens in the phasor solutions, which we commonly use in our calculations, is that when you flip t to minus t, I am flipping positive frequencies to negative frequencies. Does this make sense, right? Because your E tilde has components that vary as exponential minus psi omega t. It only has the positive frequencies. But the moment you take t to minus t, you end up only constructing the negative frequencies, right? Because exponential minus I omega t becomes exponential plus I omega t. Does this make sense, right? So when you do time reversal operation on these complex phasor solutions, then we run into a problem, and that problem is that the phasor doesn't remain valid anymore as per our original definition, which is only keep the positive components. Of course, this is just like a very technical point in the sense that there's no problems working only with negative frequencies. But if I write down a system of equations that is only valid for positive frequencies, I have to make sure that my time reversal is also always bringing me back to the positive frequencies. So how can I do this? Does anyone have a guess? So the time reversal operation is t going to minus t. That takes me from positive frequencies to negative frequency. So I want some semblance of time reversal. So I still want to do t to minus t, but I want to go back to the positive frequencies instead of landing at the negative frequencies. So what other operation can take you from negative frequencies to positive frequencies? So it's simple. It's just a complex conjugate operation, right? So a complex conjugate operation can convert exponential I omega t to minus I omega t, right? Does this make sense? So, and if your epsilon happens to be real, right? If your epsilon happens to be real, then I know that my E star and H star also satisfy the same Maxwell's equations, right? So if is real, right, then so does the complex conjugate of my phasor. So what I can then say is E star of x comma minus t and H star of x comma minus t is a valid solution of Maxwell's equations. Does this make sense? So now E star of x comma minus t is something that has come back into positive frequency. So it's a valid phasor representation. Does this make sense? So it's a somewhat technical point, but we'll be using this quite a lot. So I thought I would make this very explicit.
Could you explain why there's a minus sign on t?
But that's the definition of time reversal, right? So the statement is that if E tilde and H tilde satisfy Maxwell's equations, so does E tilde of minus t and H, oh, sorry, negative. We should have a negative sign here. So does E tilde of minus t and negative of H tilde of minus t.
And for the reciprocity, there's just the conjugate, right?
No, reciprocity is not conjugate. Reciprocity is completely different solution.
Oh.
Right. So if you come back to reciprocity, reciprocity is a relationship between two independent solutions of Maxwell's equations.
Oh yeah.
Right. So there isn't a simple operation. So as I said, like, you know, this picture that we draw here, if you don't think about it carefully, is a bit misleading. So it seems like we are reversing the first solution, but we are not reversing the first solution, right? We are constructing a completely new excitation in which I excite the second waveguide mode. Okay, we'll think about this in a minute. It'll become clearer, right? So, but reciprocity has got nothing to do with conjugation or time reversal. It's taking two independent solutions. They can be two solutions with two different sources and relating them, right? Whereas what time reversal is saying is take one solution and then flip t to minus t in it. Okay. Okay. So this is important. So this, you know, I mean, I call it phasor time reversal because that's what we are using practically, but it's, of course, it's just time reversal. So the phasor time reversal operation is essentially saying that you take E of x comma t and H of x comma t and convert them to, well, as phasors, so E tilde, and convert them to another set of valid phasors by doing.
And what's the benefit of introduced phasor?
So this will become clear in a minute, because when we write down these couple mode equations, which we'll do maybe in the next class, right? When we start writing down these couple mode theory equations, you'll see that those couple mode theory equations only make sense if you're working with phasors, like only with positive frequencies. Okay, so if I want to make sure that my couple mode equations satisfy time reversal symmetry, I have to use this phasor version of time reversal symmetry. Okay, right. So the benefit will become clearer in a minute, right? So sorry, not in a minute, but in the next class, hopefully, right? But the phasor, so a lot of simple models that we use for simulating electromagnetic systems are actually only written for these phasor representations. So we kind of need to make sure that our results are consistent with the phasor representation. Okay. Okay, excellent. So this is what time reversal symmetry looks like. Oh, sorry. And so what does this imply? So this is, of course, time reversal symmetry written in time domain, which is what we'll be using in couple mode theory, because we are studying temporal couple mode theory. So couple mode theory in time domain, but you can formulate this equivalently in frequency domain. So time reversal in frequency domain. Right. And so this just follows from the time domain time reversal. So you have if E of x comma t comma H of x comma t satisfy time domain Maxwell's equations, right? Then we have, so E of x comma minus t and minus h of x comma minus t also satisfy time domain Maxwell's equations, right? So this is a statement of time reversal symmetry, right? So this is what time reversal symmetry means, right? So which would mean that their Fourier transforms satisfy the frequency domain Maxwell's equations, right? So thus, if E of x comma omega and h of x comma omega satisfy frequency domain Maxwell's equations, okay, then the Fourier transform of these time reverse solutions are also going to satisfy frequency domain Maxwell's equations, correct? So what is the Fourier transform of time reverse solution? Well, if you remember from your Fourier transform class, that if the Fourier transform of f of t is f of minus omega, right? Then the Fourier transform, where we are working with phasors, so there should be a star here, sorry. There should be a star here. So then the Fourier transform of f of minus t star is going to be f star of omega. Okay. So this is a simple property of Fourier transform. So then you get your relation for time reversal symmetry, for your reciprocity, you give frequency domain time reversal symmetry, is that if E of x comma omega and h of x comma omega satisfy frequency domain Maxwell's equations, then E star of x comma omega and minus h star of x comma omega satisfy frequency domain Maxwell's equations. Okay. Does this make sense?
More derivation in the reader.
Sorry, say it again.
Is there some derivation in the reader?
Yeah, so I'm not sure if this is in the reader though, but yeah, so this is just like an application of Fourier transform, right? So f of t has Fourier transform f of omega, f star of minus t has Fourier transform f star of omega. That just comes from the Fourier transform formula, right? So your f of omega is integral f of t exponential minus I omega t dt, or plus I omega t dt, right? So what is the Fourier transform of f star of minus t? Something like this, and this you can show is just equal to f star of omega. Right, so it's a very simple mathematical manipulation, and that's all that we are saying here. Is that if ex comma t hx comma t satisfying Maxwell's equations imply that this time reverse solution satisfy Maxwell's equation, then so do their Fourier transforms. Right, so if the Fourier transform of E of x comma omega and h of x comma E of x comma t and h of x comma t are these, then the Fourier transform of E star of x comma omega, E star of x comma minus t is E star of x comma omega, and the same for magnetic field, right? So this is just translating the statement that we made for time domain field via Fourier transform to a statement on the frequency domain fields. Okay, so that's what's happening. So now what does this imply for the device that we have in question? So for a waveguide based device. Right. So let's consider a waveguide based device. Again, we have a bunch of input ports and we have a bunch of output ports, right? And suppose you consider one solution of electric field, so E of x comma omega, that is equal to sending in some inputs Bn plus, En plus you get some outputs En minus, right? So this is kind of what we had. Right, so your electric field is equal to Bn plus En plus forward propagating waves plus the sum of the backward propagating waves, right? So now, if your structure satisfies time reversal symmetry, right? If your structure satisfies time reversal symmetry, then E star of x comma omega should be a valid solution to Maxwell's equations as well, right? So what is E star of x comma omega? E star of x comma omega is summation Bn plus star times En plus star plus Bn minus star times En minus right? And if you remember, what is En plus star? What is the conjugate of the forward propagating mode? That is just the backward propagating mode, right? That's how we had set up our forward and backward propagating wave. If I take my forward propagating mode, it is going as exponential I beta z. If I take its complex conjugate, I will get a mode that is exponential minus I beta z, right? So I end up getting Bn plus star En minus plus Bn minus star En plus. Okay, so see what is happening here. So this conjugation is an act of applying time reversal, right? So what we are doing through time reversal is saying that the forward propagating modes become backward propagating modes in the time reverse system. And what were backward propagating modes in the original solution now become forward propagating modes. Right? So this is what time reversal corresponds to. So you send in some electromagnetic field and you get out electromagnetic field. So you send in some forward propagating modes and you get out your backward propagating modes. Time reversal means you take those backward propagating modes and you send them back into the device as forward propagating modes, right? So you're taking all the modes that are coming out and you're sending them back into the device, right? So now, because this is a valid solution to Maxwell's equations, it means that the now forward propagating modes should multiplied by the scattering matrix should give you the backward propagating modes, right? So Bn minus, or rather B minus star. So this is time reversed forward propagating modes. Right? Multiplied by the scattering matrix S should give you the time reversed backward propagating mode. Does this make sense?
Why is this question?
Well, because this is a valid solution to Maxwell's equations, right? For the same device.
Yeah.
And in this solution, these are the forward propagating modes.
Mm-hmm.
Right? And these are the backward propagating modes. If this satisfies Maxwell's equations, the forward and backward propagating mode have to be related by the scattering matrix.
Yeah.
Does this make sense? But my original solution was also a solution of Maxwell's equations. So you get Bn minus is equal to S times Bn plus. Does this make sense? So remember, we started off with a solution in which I had bunch of forward propagating modes giving me backward propagating modes related by the scattering matrix, right? From that, I did a time reversal operation and I constructed a different solution. In the time reversal operation, the backward propagating modes became the forward propagating modes. I took all the modes, all the fields that are coming as output from my device and I send them back into the device, right? So they became the forward propagating modes and I got another relationship between the forward and backward propagating modes. And you can see that if these two relationships need to be satisfied, then this immediately implies that S is the inverse of S is just equal to its conjugate. Okay, so this becomes the constraint on the scattering matrix as set by time reversal symmetry. Does this make sense? So we have three properties: unitarity, reciprocity, and time reversal, coming from three properties of Maxwell's equations. So now, can someone tell me when time reversal is going to be violated?
If we have some sort of loss in the system?
Sorry, say that again?
If there's loss inside
if there's loss in the dielectric, right? And where this comes from very simply is that in writing down this time reversal symmetry, this conjugation operation will only hold if epsilon is real, right? So the moment epsilon becomes complex, your time reversal symmetry breaks, right? And epsilon becoming complex can happen if there is any loss in your system. It can also happen if there is gain in your system, right? So if you put gain, you will again break time reversal symmetry. In fact, you can put equal amounts of gain and loss and you'll still break time reversal symmetry, okay? Because this is saying that your epsilon as a function of space has to be real. So if you put gain and loss in your device, and there is a whole class of devices that people are investigating, PT symmetric devices, which put equal amounts of gain and loss, but you can in general still violate time reversal symmetry unless you do it in a very specific way. Okay. So I'm going to leave you with one teaser, like a question that we can discuss next week. And that question, is something that I like a lot. So a very simple example of a two-port system is an interface between two dielectrics, right? So you can imagine you have dielectric with refractive index N1 and you have dielectric with refractive index N2. So this is a problem that you all have solved many, many times, right? So you send in a plane wave. So instead of waveguide modes, you have plane waves, right? Same thing. In 1D, there's no notion of transverse confinement, but everything that we have talked about holds for waveguide modes, right? So I can send in an exponential I k1x here, right? And I'm going to get some wave that is transmitted and some wave that is reflected, right? So what is the reflected wave? So the reflected wave here is going to be N1 minus N2 upon N1 plus N2 times exponential I k1x minus sign. Is this correct? Or is it N2 minus N1? I think it's N2 minus N1. Right? And the transmitted wave becomes 2N1 upon N1 plus N2 times exponential I k2x. Right? You guys have done this exercise many times, right? And similar, so you can now collect these into a scattering matrix. So you could write a 2x2 scattering matrix for your system, right? So you have, this becomes an on diagonal element, so N2 minus N1 upon N2 plus N1, right? Because it is telling you the relationship between the input and output at the same port, right? And this becomes an off diagonal element to N1 plus N2. Does this make sense? Right? I'm just writing this as a scattering matrix, right? So your two ports are, one is a wave coming in through here, the other is a wave coming in through here. So one port, second port, coming out is backward propagating is the output of first port, forward propagating in the second medium is output of the second port, right? So very similar setup. And then so you can fill up the second element, which is not very hard to do. It is just flipping N1 and N2, right? Because it's the same problem, but flip N1 and N2. Does this make sense? So this is an example of a 2x2 scattering matrix, right? I've just collected the usual reflection and transmission coefficients onto a scattering matrix. However, when you write the scattering matrix, can you tell me what this violates?
Yeah, isn't it the problem that it's not equal to its own transverse?
Yes. So why is that happening? I don't think I did anything to violate time reciprocity here, right? So I wrote down a scattering matrix for a 2x2 device, right? Which is just a dielectric interface here, and you immediately notice it's not symmetric, right? Which means I'm violating reciprocity, but that seems odd because I literally just put two materials next to each other. Does anyone have a quick answer to this? Or maybe you guys can think about this and give me the answer next class.
It seems like there's an asymmetric spatial distribution of the dielectric. So
why should that matter?
It depends on the polarization, I think, of the E field.
But this is a 1D problem, so you can assume any polarization out of plane. You can assume polarization like this.
Maybe
Is
the
it
energy.
because the permittivity is ill-defined at the boundary? Exactly.
No. I mean, that's fine. You always have discontinuity.
It's like your mode normalization, right?
Right, exactly. Thank you. That was quick. Last year, people didn't get this quickly. Yeah, it's mode normalization. Remember, all of our derivation is done assuming you have unit power in my modes. On the other hand, the amount of power in a plane wave with unit amplitude scales proportionally to the refractive index. Okay, so what you need to do is, for your modes to be correct, you need to divide this by 1 by square root N1, and you need to divide this by 1 by square root N2, right? If you make this correction, what you end up getting is square root of N1 and 2, perfectly symmetric. So breaking reciprocity incorrectly is very easy. A lot of people have broken reciprocity incorrectly in our field many times, but breaking it correctly is very hard, right? So this is one simple example of how not accounting for powers correctly can result in your reciprocity breaking. So this is not actually reciprocity breaking, but so this is just trying to solidify the fact that when we wrote down the scattering matrices, we are assuming that the total power in our individual modes is normalized to the same quantity, which is here. Okay, right. In fact, you could take in the matrix that I wrote there, and you could have seen that it also violates energy conservation, which obviously doesn't make sense. It's because you didn't normalize properly. Okay, so we'll stop here. So we are done with like the parts in which I wanted to talk about the scattering matrices of my devices. So maybe this was a repeat for many of you, new for some of you. So I would suggest you go through this material again if you haven't seen it before, and if there are any questions. Now, next class, we'll start developing models for cavity waveguides using some of these concepts that we talked about today. Okay, yes, see you guys on Monday, then also Tuesday. And yeah, sorry, I couldn't take office hours yesterday, but I'm going to do them tomorrow from 3 to 5 if you have any questions. Okay, all right. So yeah, so I'll stay online for a few more minutes. You guys can start leaving, or if you have any questions, we can talk about it.
Thank you.